So what we have here is a picture of a box of Matthys cereal. And we're going to have the random variable x represent the weight of cereal in a box. The company Matthys might make millions of these boxes, and there might be an expected value of the weight. So the expected value of the weight of the cereal in the box, so not counting the box itself, let's say that this is 16 ounces. And you'll often see this type of thing written on a box, 16 ounces. Well, that doesn't mean the cereal in every box is exactly 16 ounces. There's going to be some uncertainty here. The density of the flakes matters, how it happened to be poured in. The boxes, the size of the flakes, the weight of the flakes might make a difference. And so let's say in this situation, the variance of x is equal to 0.64 ounces. I'm just picking a reasonable number to show that, look, there's some uncertainty. It's not going to be exactly 16 ounces. Similarly, let's assume that we have a bowl. And let's say that and we want to have the random variable y that represents the weight of cereal in the bowl. And once again, there could be some expected value of our random variable y. Let's say we know that on average, the mean or the expected value of y right over here is going to be 4 ounces. But once again, there's some variance depending on the size of the flakes. There's some variance depending on who's pouring it, when they decide how close we are to the top. So let's say the variance of y is equal to 0.36 ounces. So with that as a setup, now let's think about the sums or the differences of these random variables. So let's consider the sum. Let's say we have a new random variable that's the sum of x and y. We could say this is some random variable z. We know from previous videos that if you take the expected value, you would just take the sum of the expected values. So the expected value of x plus y is the expected value of x plus the expected value of y. That makes sense. If you were to say how much cereal is in this, how much cereal in total, if you talk about all the cereal in this box plus the cereal in this bowl, well, you would expect it to be 16 plus 4 ounces or 20 ounces. Similarly, if you said, well, what is the difference between the weight in a box and the weight in this bowl, you would expect to find the difference between the expected values. But now we're going to think about variance. So first, let's think about what is the variance of our random variable x plus our random variable y. What do you think that is going to be? Well, it turns out that you would indeed add the variances of each of the random variables, assuming that they are truly independent, that the probability of getting a certain weight in this bowl right over here isn't dependent on what weight you happen to have in this box over here, if we assume they are independent. So let me write here, assuming independence right over here. And in a future video, maybe in this one if we have the time, I'll give an example which hopefully makes it a little bit more intuitive why this independence assumption is important. And this makes sense. You have some uncertainty here, which you could measure with the variance, and you have some certainty here. So if you're taking the sum, you would sum the uncertainties at least measured by variance. Now I'll ask maybe an even more interesting question. What if you had a random variable that was the difference? That was the difference between the two. What would this be? Well, with expected value, we just took the difference of the expected values. But it turns out that with variance, you will still sum the variances. And one way to think about it is, you have some uncertainty here, you have some uncertainty here. If you add or subtract, the uncertainty only builds in that situation. You could view this random variable as, let's take a random box of our Matthys cereal. Let's open it up. So I'm going to open up the box right over here. I have some cereal in there with a mean weight of 16 ounces. And I have an empty bowl, which on average has an expected, I guess you could say, carrying capacity of 4 ounces. And I were to take some of that cereal out there. And for the sake of argument here, the amount of weight of cereal that ends up getting poured in right over here is completely independent of the amount of weight that is originally in this box. Well, in this case, x minus y would represent the amount of cereal that's left in that box. And think about the variability there. There's the variability that we started with. How much did we start with? And then it depends on who's pouring, how it's poured, maybe the wind patterns as the flakes are falling in there, that you would only add more variance. So another way to frame this, if we want to think in terms of standard deviation, remember, the variance is the standard deviation squared. So we could write this as the standard deviation squared of the combination of two random variables is equal to the sum of the squares of the standard deviations. So the variance of random variable x and the variance of random variable y. And this might look a little bit familiar. You're familiar with the Pythagorean theorem where a squared plus b squared is equal to c squared. And that's why this is actually called the Pythagorean theorem of statistics. And there's very interesting ways to think about it in terms of a right triangle. If we have two random variables that are truly independent of each other, then we could have our, for a right triangle, you have to have a 90-degree angle between the sides. Here you have independence. And there's actually ways to connect these ideas geometrically. But you can see it right over here that you wouldn't just add standard deviations, you'd add the square of the standard deviations, or you would add variances. It's very important to keep in mind. And once again, just to rephrase the second part, even if you're looking at the variance of the difference of the variables, you still will add the variances of each of these variables right over here. So to make this case concrete, in either situation, if we're talking about the sum of a full box and a full bowl, the variance of that sum is in this case going to be the sum of the variances, which would be 0.64 plus 0.36. So in this case, the variance of x plus y is going to be equal to 1 ounce, which is going to be equal to the variance in the other case, if you were to find the difference between x and y. Either way, it doesn't matter that you're subtracting, the variability, the uncertainty will continue to build. And if we wanted to express this same idea in terms of standard deviations, the standard deviation of our variable x is what? It's the square root of this. It's 0.8 ounces. And the standard deviation of y here is the square root of this, which is 0.6 ounces. I would say, okay, let me square this. So I get my 0.64 here. Let me square this, and I get my 0.36. Let me add them together. I get my 1 ounce here, which is my variance. But then I would take the square root of that, and I would get that the standard deviation, let me write it over here, the standard deviation of x plus y would be the square root of our variance, which is still, based on the units we're using, still 1 ounce. So notice, those did not add up. 0.8 plus 0.6 is not 1, but if you take the sum of the squares, it does equal 1 squared.